Alright guys, so an application of what we were talking about last would be something called an RC filter, and it looks very similar to um, the circuits we were looking at before. So we're going to have an AC signal source with some voltage peak to peak and some frequency, and we could have a resistor first and then a capacitor, or we might have the capacitor first. So one way to think of these RC filters is that they're frequency dependent voltage dividers. And the reason I say that is because the impedance of the capacitor depends on frequency. And so the overall resistance of the circuit depends on frequency, and the voltage drop across the capacitor will depend on frequency. If you remember, the voltage out for a voltage divider was equal to the voltage in times RB over RA plus RB, if I had a circuit that looked like this, where this is RA and this is RB. So for RC filters, it's very similar. The voltage out, peak to peak, is equal to the voltage in peak to peak times the impedance of the second thing over the magnitude of the impedance of the two added together. So in this case, let's take the first circuit as an example. Let's say I have a voltage of 5 volts peak to peak, a frequency of 1 kilohertz, and let's say that I have my resistor first and then a capacitor. And the resistor, let's say, is 1K and the capacitor is 10 microfarads. Then the voltage out, peak to peak, and remember, the voltage is going to be changing because we're going to be putting an AC signal in. So that's why we're referring to peak to peak, which is twice the amplitude of, say, the sine wave or whatever we're putting in. The voltage out, peak to peak, is going to be equal to, in this case, 5 volts peak to peak. The impedance of the second thing, which is a capacitor, so that's its reactance. That's 1 over 2 pi frequency times capacitance, divided by the magnitude of the total impedance. And so that's the magnitude of the resistor, 1K, plus 1 over 2 pi frequency times capacitance, J. Or we could write this a little bit differently. If we found what the reactance was equal to, so 1 over 2 pi Fc. So let's calculate that real fast. So in this case, we're going to have 1 over 1,000, 10 microfarads. We're going to get the 15.9 ohms that we got in the last example we did together. So that means that this is 15.9, sorry, the voltage in is 5 volts peak to peak, times 15.9 divided by 1,000, sorry, the square root of 1,000 squared plus 15.9 squared. And we can type that into our calculator to see what that's equal to. So we're going to have 5 times 15.9 divided by the square root of 1,000 squared plus 15.9 squared. And I'm missing a curly bracket. 1 second. There we go. And so the voltage out is significantly reduced. Our voltage in was 5 volts, and our voltage out is 0.08 volts. We can do another example where we flip this around. Let's see how this circuit behaves if the resistor is second. So I'll have the capacitor first, and then the resistor. We'll keep everything else the same, so it'll still be 5 volts peak to peak. Frequency will be 1 kilohertz. We'll have, this will be the 10 microfarad, and this will be 1K. In this case, our voltage out, peak to peak, is again, it's the impedance of the second thing over the magnitude of the total impedance, which in this case, is the impedance of the second thing is 1,000, divided by the magnitude of the total impedance is going to be the square root of 1,000 squared plus 15.9 squared. And, oh, sorry, I left out the voltage in peak to peak, 5 volts there. Alright, we can calculate that. So really the only difference is the term on the top is not the reactance of the capacitor, now it's the resistance of the resistor, and we're going to get just about 5 volts. So just about everything comes out. So in this situation, if the frequency is very slow, then the capacitor the capacitor will have a high impedance. Which means most of the voltage drop will be across the capacitor. And so we'll get a signal out. And so this circuit is called a low pass filter, because the voltage coming out will be relatively unaffected as long as the frequency is low. We saw the opposite of that. We gave it a relatively high frequency, and we saw that it attenuated or reduced our voltage out by quite a bit. So this circuit, the first example, is a low-pass filter. The second circuit, we gave it a high signal again, and because the frequency is high, there's not going to be very much impedance caught from the capacitor. We saw that the capacitor's impedance was only about 15 ohms. So most of the voltage is going to drop across the resistor, and that's why we got virtually all of the signal out. And so this is considered a high-pass filter. High frequencies are allowed to pass without being reduced. You guys have some homework on the following page where you should try to calculate the voltage out for the following circuits.